Computer. Hey, Don. Thanks for joining us.
Thank you, Matt. Thanks for your kind invitation.
No problem at all. I'm just going to try and get sort of straight into the meat of this, really. And what would be quite helpful, I think, for some of our members, if you gave a kind of intro to your theory of conscious realism. And I mean, am I right in saying that you regard yourself as a conscious realist?
Yes, and the idea there is quite the opposite of the standard view about consciousness today. So most of my colleagues, I would say 99% of my colleagues studying consciousness assume that space and time are fundamental and that consciousness is a latecomer in space-time, that at the Big Bang there was no consciousness, and it probably took millions, perhaps billions of years before life emerged, and even after that, before consciousness emerged. And so they're looking for substrates inside space-time, maybe neural or AI kind of architectures or whatever that might give rise to consciousness. So their idea is that whatever consciousness is, it somehow emerges from other properties of a substrate inside space-time. And the remarkable thing is, of course, that these series of conscious experiences have, well, there's estimates that we have billions of specific conscious experiences, colors, tastes, smells, and so forth. And if you ask how many of these, there's billions of them. So it should be like shooting, fish in a barrel. So how many have they shot? How many theories of specific conscious experiences do they have?
Mm.
And the remarkable thing is zero.
Yeah.
There are zero conscious experiences that have been explained this way. And these people are not dumb. They are my friends. They're my colleagues. They're brilliant, and some of them are geniuses. So I decided to start looking in a different direction.
Just briefly on that, Don, is this where you challenged Stuart Hameroff? I think you gave a bit of a sort of some narrative around this, and said that apparently you've challenged him again and again and again, and he still hasn't been able to deliver any explanation of qualia.
And Tononi. Well, yeah, I've asked this question of Tononi, and I'll ask it of any physicalist. I mean, and again, all in good. Then we'll go have a beer together, right? So it's
yeah.
So there's nothing personal in this. I mean, we're trying to solve a problem, and I'm just saying, yeah, I agree. We want to solve this problem, and that doesn't seem to be the way to solve it. And tell me if I'm wrong, right? But if you've got the solution, please tell me. If not, we've been working on this for several decades now, and you guys aren't dumb. You guys are brilliant. Maybe we need to, maybe we got stuck in a frame of mind for solving this problem. That's the wrong frame of mind. We need to step out of the box and look around for other approaches.
Yeah.
So the approach that I'm taking, which is very, very different, and one reason why I mentioned what I did up front is that most people just assume that the physicalist point of view is, of course, the correct view, and anybody else's is clearly the burden of proof is on them. And I just want to make clear that the burden of proof is on the physicalists. Right now, they're batting zero. So they don't have the assumption that they are on the right track. Understand that they have zero specific conscious experiences that they can explain. And we can talk about Tononi's idea about space and his paper on the perception of space and so forth in this theory, if people are interested. So what I'm doing now to answer your question, to get to your question, I'm saying let's reverse the game. Instead of starting with space-time and physical objects or substrates inside space-time and trying to boot up consciousness, let's go the other way around. Let's start with conscious experiences. Every theory has to start with something. You always have to make certain assumptions, then you explain other things.
Free miracle.
Right now, the physicalists are assuming space and time, they're assuming physical objects, they're assuming the laws of physics, and then they're having to stipulate the conscious experiences because they can't explain them. So they have to stipulate them as well. So I'm saying, well, you're stipulating everything. So I'm going to only stipulate the conscious experiences, and then I have to explain space-time and the laws of physics. So if I can do that, then I've actually won according to Occam's razor, because my theory stipulates stipulates everything.
Yeah, because philosophically, you're building on the one thing that we can be certain of, echoes of Cartesian thinking here. I think, therefore, I am. That's the one thing that we know, and that's that. You're using that as a foundation to do the rest of the work.
Well, yes, although
I mean, I know he's a dualist, right? So I know he went down the wrong path, but he had something there, didn't he? That's the rock of the foundation. So if conscious experience is real, and that's perhaps our free miracle here, then build on that instead of the assumption that matter is real. But how do we get them out of this paradigmatic way? How do we show that they're in a paradigm and that their very language is constraining their thinking? How is that done? I mean, obviously by popularizing these sorts of ideas and trying to go against it, but it must take some real courage, Don, to do that.
Well, that's what tenure's for.
Mm, mm, mm.
I mean, and that's partly a joke, but it's partly quite serious. I would not have attempted this before tenure, but
Right.
after so tenure is not there to make people have a nice, cozy life. It's there to allow you to be brave and challenge the orthodoxy in your scientific or other field, in academia. So hats off to that. Without that, people like me would probably, you have to feed your family, and so you might be smarter not to go after this stuff.
Yeah. Yeah.
So, so what was your question now?
Yeah, it was. Yeah, there was kind of mixture of things there. It's kind of like, what's it like working among people that's kind of, think you might be a bit crazy. From my own limited experience of this, when I did my philosophy degree, I would say they were nearly all logical positivists. So for their metaphysics was just completely off the table. I wanted to do my dissertation on Berkeley, the renowned idealist and so on. I've always had a kind of inkling towards idealism. So it's just really refreshing to see a scientist come forward and say, actually, this might be the case. This actually might be the case. These intuitions and even those mystical kind of insights and stuff actually may have some sort of logical ground.
They might, and actually, yeah. And as you were asking, so what kind of arguments could I give towards supporting this kind of approach and taking consciousness fundamental? And one, or at least not taking space, time, and physical objects as fundamental. And so I have two approaches on that. And they both are based on an important fact about science. Every scientific theory, and this is going to sound unbelievably simple and trivial, but it's very important. Every scientific theory makes assumptions, and if you grant those assumptions, it says, I'll explain this other great stuff. Sounds trivial, but it's not trivial, because that means the theory doesn't explain its assumptions, it assumes its assumptions. That means there is no theory of everything, in principle.
There can't be.
You can always try to get a deeper theory that explains the assumptions of one theory that you have, but that theory will have its own new assumptions, and this goes on ad infinitum. I take that to mean that there will be no scientific theory of everything, ever, and that it's really an infinite regress. I'm seeing an infinite regress here. That means that as far as we know, we are infinitely far from even getting close to anything like a theory of everything. So we should be extremely modest and humble in the statement of our scientific. We should be saying, these are the best that we have so far. The relationship of this to objective reality, even if we pass all these experimental tests, that doesn't mean that this is the theory of reality. This just means that we haven't been smart enough to find out where it mismatches from reality.
Could we say that we can be less wrong?
Well, it might be that we can be less wrong about a perspective on reality, but I'm not sure if we ever say that we can be less wrong about, I just, because how do you know what reality is? I mean, it's concepts. So so what we can say is, from this perspective, using this set of concepts, this theory goes so far. And that's going to be my point here. And that is that every theory, a good theory, will have a scope, a set of things that it can explain, and it will have limits. The end of explanation. That follows from me saying that there's no theory of everything. There's going to be something it can't explain. Now, a good theory gives you mathematical tools to explore its scope. A great theory gives you mathematical tools to find its limits. So Einstein's theory of space-time, incredible theory, right? Good theory because it gives us all this wonderful exploration of space-time and the concept of space-time, and we use it in GPS and all this, it's incredible. But it's great theory as well because it tells you the mathematics of Einstein's theory is part of the proof that space-time itself, that concept, falls apart at the Planck scale, 10 to the minus 33 centimeters, 10 to the minus 43 seconds. That is a hard limit to Einstein's theory, and his own mathematics tells you that. So already there's two important points there. One is we can use scientific theories and their mathematical logic to actually, for great theories, we can use the logic of the theory itself to find its limits and show that even the fundamental concepts like space and time, nothing more fundamental to Einstein's theory than space and time. His theory shows that those concepts themselves have hard limits. 10 to the minus 33 centimeters, end of the story. This theory is done. There's no operational meaning to it. So that's one incredible point here. But the other incredible point is that means that space-time is not fundamental. And objects inside space-time, I mean, fundamental particles like bosons, leptons, and quarks of the standard model, what are those theories? What are those particles? They are technically known as irreducible representations of the Poincare group of space-time. They're, in other words, the particles that we see are a reflection of the space-time that we use. Mm. They are symmetries. They are representations of the symmetries of that space-time. So what are my colleagues trying to do when they boot up a theory of consciousness from physical substrates? They're saying, we assume that space and time are fundamental, and that the particles of space and time, and the bosons, leptons, and quarks of the standard model, those are the fundamental elements of reality. They really exist, whether or not they're perceived. They have real causal powers, and when they have the right kinds of causal structures or functional structures, then consciousness emerges. And I'm saying every bit of that story is false. Space-time is not fundamental. The particles don't exist when they're not perceived. They're just representations of the symmetries of space-time. They have no causal powers. So the whole thing, the reason why my brilliant, and again, I am in no way denigrating my colleagues. They're brilliant. They're geniuses. Most of them are so smart, I can't even figure out how smart they are. But when you have the false foundation that space-time is fundamental, there's no way, it doesn't matter how smart you are, you just can't do it. So that's why I'm now saying we're going to have to go the other way. But that's one argument so that's the argument from high energy theoretical physics. The conclusion that space-time is doomed, that space-time is not fundamental, is the conclusion of physicists like Nima Arkani Hamed, David Gross, and others. But that it's a special group of physicists called high energy theoretical physicists. So if you ask a standard physicist who's doing, condensed matter or whatever, they may not even know about this. Right? That's not their area. So it's high energy theoretical physics. Now, the other pointer to answer to your question is not only does high energy theoretical physics say this, but evolution by natural selection agrees. And this is where I've done a little bit of work. I would first point to some work by Steven Pinker in his book, How the Mind Works, and a paper that he wrote, So How Does the Mind Work? And what Pinker points out that there are all sorts of selection pressures for us not to have true beliefs, including true perceptual beliefs. We try to do things where evolution shapes us to be fast, and have heuristics that don't require a lot of computational energy to execute and so forth. So there are all sorts of reasons why we would take shortcuts and heuristics. But Steve thought that maybe we did have good access to true properties about everyday middle-sized objects, tables and chairs, forks and spoons, and so forth. And so I went after that one. I looked at that. Basically I was following Steve's idea, but I wanted to see, are there any exceptions, or is it really the whole shooting match? And what I found to my amazement was that when you look at evolutionary game theory, which is the mathematical foundations of Darwin's idea, that mathematics tells you very, very clearly that the payoff functions that govern the evolution of a system, including its perceptual systems, its sensory system, the payoff functions almost surely do not have information about the structure of the world. And almost surely is a technical term. It means essentially with probability one. With probability one, they don't have information about the structure of the world, so they couldn't shape an organism to have sensory systems that tell them about the structure of the world. Now, I've had a couple responses from colleagues in my field and philosophers on this. From philosophers, it's, Hoffman, you shot yourself in the foot, logically. I mean, Darwin's theory assumes that there are real physical objects like tables and chairs and organisms and resources in space and time. And so if the mathematics of evolutionary game theory says that that's not the case, if that space and time and physical objects are not fundamental,
Mm.
there's two horns of this dilemma. Either the mathematics of evolutionary game theory faithfully represents Darwin's ideas, or it doesn't. If it doesn't, of course, you shouldn't use it to do this. And if it does, it couldn't possibly refute Darwin's basic fundamental ideas.
Yeah.
So either way, Hoffman, you're in an unfortunate dialectical situation.
Mm.
In other words, you shot yourself in the foot, and you should probably take some philosophy before you start doing science like this. Bad.
It's Tallis, isn't it? Tallis had these
Tallis
similar objections. Yeah.
And Bagwell.
They're saying, hang on, you're doing your reasoning within this space-time framework, so therefore you can't disprove the existence of space-time. But do you want to explain? Do you want to explain to us why that's foundationally wrong?
Well, yes, and that was sort of why I started off by talking about
yeah.
theories having assumptions and then their conclusions, and that a great theory gives you the tools to show the limits of that theory. So all I'm doing is doing essentially what people do with Einstein's theory, right? They use the mathematics of Einstein's theory to point out, well, it falls apart at 10 to the minus 33 centimeters.
Yeah.
No surprise, every scientific theory has its limits, period.
Mm.
And one of the brilliant things about science is most of our informal theories, of course, they're going to have their limits, but they're so informal you can't figure out what the limits are. And so you can talk BS where you don't even know you're talking BS.
Yeah.
Whereas with a good scientific theory, it gives you the tools without shooting yourself in the foot logically to find the limits of the very concepts that are the foundation of the theory. And so the argument is now I'm not saying that it's not possible to refute yourself. It sure is, but it's not necessary that you are refuting yourself when you take a theory and use its own mathematics to show the limits of those concepts. And and Gödel was not refuting himself when he used axioms of arithmetic to show the incompleteness of those very axioms. He did that without self, and that's all. I'm basically the same kind of idea, but in a different framework. Mathematical theories in science surely have the power of arithmetic, and so they're subject to Gödel's incompleteness.
Yeah.
Period.
Yeah.
And so
provably. Yeah.
Yeah. Provably. So that's why I'm not shooting myself. Well, why I'm not necessarily shooting. Yeah, you can still go back and look at my logic and say, well, yeah, even though it's not necessary that you shot yourself, you did shoot yourself in the foot. So people can do that, but the a priori arguments don't hold.
Can I just check something there with you, Don? Because for me, it doesn't seem as though you're denying that there's something there that can be described with evolutionary theory. There is some phenomena there, but you're just saying it is not standalone, extensible, physical stuff in space-time, right? So it's probably the results of some other form of mentation or some other conscious agency that we're rubbing up against. So that brings me to an interesting kind of question, actually, because you've often talked about this idea of, when you're not looking at the moon, it's not there. But can I just refine that a little bit? Can I ask whether, presumably, you think there is something there that looks like the moon that continues on when we're not looking at it? Or are you going even further than that and saying that there is literally nothing there at all when it's not being perceived?
Yeah, I think there's something there, and the relationship to my experience of the moon is completely arbitrary. So, for example, to give you an idea, just a metaphor for how I'm thinking about it, if you're playing a virtual reality game like Grand Theft Auto with a VR headset on and so forth, and you look over and you see a red Ferrari, and you're racing a red Ferrari. Well, in this metaphor, the reality is some supercomputer. And what you're really doing is toggling voltages at millions of voltages per second, or billions per second in some supercomputer. If you looked inside that quote unquote reality, you wouldn't see a red Ferrari anywhere. So the red Ferrari, of course, is related to those voltages and their toggling rates inside the supercomputer, but there's nothing red, and there's no Ferrari, there's no steering wheel, nothing like that in the computer. That's how different our perception of the moon is from whatever the reality is that is triggering us to have that experience.
And that reminds me, just briefly, Don, sorry, that reminds me of something else really interesting you said, that actually it might be the case when we're looking at phenomena that doesn't do it, like looking at a stone, right? It might be the case that there's more going on there, but we just because it's irrelevant to us for survival purposes, we haven't honed in on it. There was no payoff function involved in actually understanding what phenomena is really going on there. So that it could be that there is something a hell of a lot more interesting than a pebble on the beach, but we can't know, can we?
That's right. That is a good argument from evolution. Notice what we're doing there, though. We're saying, for sake of argument, let's assume, for sake of argument, that we're going to take evolution as our framework and those assumptions. We already know that if space-time is doomed, there's going to be a deeper sense in which evolutionary theory is doomed. But what you have to do as a scientist is say, let's assume this framework and see what it says. And then I agree with you. In that framework of evolution, the argument would be evolution on its own terms would say there are selection pressures for us to not know what we don't need to know to stay alive. And I don't need to know the atomic structure of a stone or of the carrot that I'm eating to eat the carrot and successfully get the nutrition. So since there are that will not increase my fitness, then now I should say, so I'm not about debunking scientific theories. I'm not trying to debunk evolutionary theory. Let me put it on the table. I think Darwin's theory is incredible. It's a beautiful theory, and inside space-time, I have seen no theory that comes close to the power of Darwin's idea and to the power of evolution to explain human behavior and human perception and the perception. So it's if you are trying to understand biology in space-time terms, then I would say go with Darwin. There's nothing that competes. But if you're saying, if your attitude is, oh, Darwin is the final word, I would say no theory is the final word. There's nothing special about Darwin. I'm not tuning Darwin. There is no scientific theory that's the theory of everything. And if you think otherwise, you will look quaint in a century. Science will have moved on, and your addiction to a particular theory will just look quaint.
There's a certain irony here, isn't there, Don? Because it seems like the most successful and productive scientific theories are the ones that we end up dragging along like a ball and chain for even, you sort of, materialist mechanistic physics gave us steam locomotives, planes, trains, and automobiles. So, it must be true, so, the kind of the model that supports these industrial endeavors and so on and so forth must be a real model. And so there's the temptation, is it? And that's that's some reason for people clinging on to these old kind of these old models. But
I agree. But I would agree, and I would say that seems to be a pattern that we think that we now have. We're close to the theory of everything. We either have it or we're that close to it. And I think that this is not merely a scientific foible. I think it's something about the human mind that we mistake concepts for the reality. Concepts are just concepts. They're pointers to the reality, but the reality, not only does reality transcend any of our scientific theories, reality transcends any kinds of concepts or words that we might want to use. Again, I'm not saying I'm against words and concepts. I use them all the time. You just have to have, prudent understanding of the limits of what you're doing. Including when you put concepts on yourself and others, right? When we actually label ourselves or label others instead of just being with ourselves and being with others, we're missing the reality that's hiding behind our concepts. So this thing about being tied to our theories and not being able to let go of them is very, very personal, because we have theories about who we are, and we can't let go of those. And so this is not just about science, it's about actually personal understanding and development.
Crikey, yeah. So it's kind of like it's about sort of looking in, isn't it? It's sort of turned obviously the obsession with space-time, because it's been such a successful paradigm frame of reference. We're looking out there, looking for the answers inside this kind of space-time manifold. But obviously, you're kind of sort of turning it on its head and sort of looking within and saying, well, actually, what is going on with consciousness and being? And could we talk a little bit about that bridge building that you've mentioned? And that's something that's just fascinated some of our members. The idea that you've come up with a kind of sort of mathematics to model conscious agents, and I think there's some sort of Markovian matrices and things like that, and you're then mapping that into the decorated permutations, and there's a mathematical means of. Some of this is way beyond me. I'll be honest, but then mapping into these amplituhedra, which can be used to do the scattering amplitudes and stuff in an actual particle accelerator. So you can
Yes.
actually now empirically within this space-time manifold, you can test the efficacy of some of your conscious agents. I mean, I just wonder where you are with that now, because that would be absolutely phenomenal, wouldn't it?
Well, yes, absolutely. And I should say that, turnabout's fair play. What I said at the start about the physicalist approaches was, show me your empirical predictions about specific conscious experiences. You can't do it. Well, then why should we? So fair enough to turn that right back on me. So Hoffman, you're saying you're starting with this notion of conscious experiences and conscious agents with these experiences outside of space-time. How are you going to give me a testable prediction that we can, find out? We're trying to do science here, not hand waves. I mean, the philosophy is fine, but what we're trying to do is science here. This is not philosophy. And so what I'm trying to do then is to start with a mathematically rigorous theory of consciousness, and I can go into it. Basically, I should say what you have to do is try to find the minimal set of assumptions to build up your theory, right? This is Occam's razor. Use the minimal set of assumptions and get the maximal explanatory power out of them. And so I just assume with my colleagues, Chetan Prakash and others that I've worked with, that two aspects of consciousness that I'm going to put in my theory as foundational. There are experiences and there are probabilistic relationships among those experiences. If I experience red now, there's some probability that I might experience green next, or that you might experience green next. That's it. So learning, memory, problem solving, intelligence, the self, free will, none of those go into the fundamental assumptions. Those all have to come out. But what we can prove, so what we do is we model those two key ideas. There are experiences and probabilistic relationships among them. We model them with Markovian kernels, and something in a structure we call a conscious agent. And it's trivial to prove that we get this like a social network of these interacting conscious agents. And it's trivial to prove that it's computationally universal. These Markovian kernels, even though they're only about quality experiences and relationships among experiences, no self, learning, memory, problem solving. We can build anything that a neural network can build, we can build with a network of conscious agents. So anything that you can do with ChatGPT, you can do with a network of conscious agents.
Wow. Okay, that's cool.
So that means that, I mean, we have enough to do anything but our foundation is very, very simple. So the question then is, how do we then predict something of interest inside spacetime? And what are we going to predict inside spacetime? And why am I trying to predict something inside spacetime? That's the first one I'll answer. Inside spacetime is the only place right now where we know how to make precise and repeatable measurements. So that's why I'm trying to get something inside spacetime, because otherwise I can't test my theory.
Well, space-time is in ours, isn't it? Space-time is in consciousness, right? So it's still a valid.
Right.
Is that fair?
It is. That's right. So for people to really see how radical this idea is, we normally think of ourselves as little 80 kilogram, 50 kilogram objects inside a vast universe that's billions of light years across. So we're tiny. I'm saying wrong. That entire universe is inside you.
Yeah.
It's in fact, it's a trivial data structure that you use. It's actually one of the more trivial data structures that you could have used. It's only got 4 dimensions. Why not 20 billion dimensions? So it's actually a trivial data structure. So the mind shift here is not a trivial one. It's you need a stiff drink before you really go after this one. So that's why I'm going into space-time, is that that's right now where our technology allows us to make predictions that we can tests of predictions.
Yeah.
So how am I going to get that map into space-time? Well, I'm lucky. The high energy theoretical physicists have, in just the last decade, said not only space-time is doomed, but they've said we need to find what's outside space-time, or at least take our first baby step outside of space-time. And in the last 10 years, they've done that. And they found, remarkably, I mean, who would have predicted this? these geometric objects that they call positive geometries, amplituhedra, associahedra, and so forth. So they stepped outside of space-time. I'm thinking of space-time as not reality now, it's just our headset, right?
Yeah.
We're consciousnesses that are using a headset to interact with other consciousness, because the whole realm of consciousness is this infinite social network. It's too complicated. So space-time is just this dumbing down headset.
Yeah.
So we've taken the headset off. For the first time, science has taken the headset off in the last 10 years and looked around
Mm.
using mathematics, and they
Mm.
found obelisks, these geometric objects sitting outside of space-time, like 2001: A
Yeah,
Space Odyssey.
yeah. It reminds me. Yeah,
Right,
the
right. So
apes. Yeah.
there's the obelisk, and all the apes are beating on it. They're hooting and hollering. They know it's important. It's really,
Mm.
really significant, and they have no clue what it means.
Don, how did
Well,
they
that's what we
find
are.
it? How did they find these positive? I mean, because I know that they do. You can do better, more elegant mathematics with this, and it gives you better predictions and so on and so forth. But how did they encounter it? I mean, were they just playing around? I mean,
Well, it's really quite interesting. This genius named Ed Witten at the Institute for Advanced Study at Princeton, and some of his postdocs discovered what are called the BCFW recursion relations. These are a mathematical tool that they discovered allowed you to compute scattering amplitudes in a way that was different from the typical Feynman diagram kind of approach and
mm,
Feynman intervals.
yeah,
And it simplified things, and it had some really interesting structure to it. And then a guy named Andrew Hodges came along and said, you know what? It looks like the new BCF, they call them BCFW recursion relations, for the names of the people, the W
yeah,
stands for Witten, for example.
right.
These BCFW recursion relations, they seem to be, in certain cases, he said, they seem to be like tiling some object. There's some geometric object, and it's the volume of this object that's giving you the probability or the amplitude for this scattering process, like two gluons in, four gluons out kind of thing.
Mm,
And so then a guy named Nimar Kani-Hamed and some of his collaborators, including Yaroslav Trinka in particular, took up Hodges' hint and said, well, let's try to find what that object is that Hodges suggested was there in this special case. Maybe it's there in general. And so they spent, a few years, worked on this problem, and discovered something called the amplituhedron, which did exactly what Hodges. So you can see it wasn't like one
mm,
genius. It was like, Witten and his team of postdocs made this incredible mathematical discovery. Hodges then had this incredible intuition that there was
mm,
some geometric object for at least some cases.
mm,
And then Niemann and Yaroslav went after it, and got this amplituhedron, which then covers. Now, it's not for all possible scattering; it's for n equals 4 super Yang-Mills kinds of scattering. But it's an important class, and it's a toy theory, but it's a pretty good toy theory, right? So, and since then, in the last 10 years, they've then been, you know, going to deeper and deeper understanding and other scattering processes.
mm.
At first, it was for massless. Now they can do massive particles and so forth. It's so big now that the European Research Council recently announced a 10 million euro initiative called Universe Plus.
Right.
It's 10 million euros. The international team, they just had in February their first conference, over 100 mathematicians and mathematical physicists. And the goal of this project is to replace space-time and quantum theory.
Wow.
They're looking for these new positive geometries
Mm,
outside space-time and quantum theory. And by the
mhm,
way, that's a key point. It's not only that space-time is doomed, quantum theory is doomed.
mm.
Quantum
Relativity theory is
theory.
doomed. Yeah. I mean, yeah, just yeah.
So we're in this
Mm,
beautiful new territory.
yeah.
Positive. So here's what I'm doing. I'm saying, okay, the physicists, they know now how to map from these positive geometries outside of
Mm,
space-time into space-time to get back testable predictions. They can actually,
yeah.
predict the scattering amplitude. That's incredible. So here they've already done a huge chunk of the work. They've
Mm,
stepped outside space-time. They found these positive geometries. But the question for them is, there's no dynamics. These are just objects sitting out there. Why? Did God say, let there be obelisks? And that's it's clearly, usually physicists want some kind of dynamics.
Yeah,
So
yeah.
dynamics, we have a
Mm.
Markovian dynamics of conscious agents outside space-time. So I said to my team, what we need to do is take our dynamical systems and show how the positive geometries arise from them. If we can do that, then we go all the way in. And so, one thing that the physicists have found is a way to, so they found positive geometries, but they found these combinatorial objects that give you insight into the structure and the ways to classify these positive geometries. And they're called decorated permutations. And it's a permutation, is just a shuffling. Like if you have the numbers 1 through 10, you can shuffle the order, and that's a permutation.
Mm.
A decorated permutation is just a little addition. Sometimes a permutation might send a number to itself, like it might send 3 to 3. Okay, so that would be, a fixed point of the permutation. Well, they allow two different ways that a number can go to itself. So 3 can go to itself in the standard way, and there's a second way that it can go to itself. Effectively, it can go to itself plus 10 in this example. So that if you want, we can go into it in more detail. I just want to give a flavor for the decorated.
Yeah.
But anyway,
Yeah.
so there are these decorated permutations. They classify the objects. And so I realized if I can map these Markovian dynamical systems onto decorated permutations, that should then give us some idea, because they classify these geometries. So that would give us some idea about how to begin to think about what parts of the Markovian dynamics should be thought of as going with what parts of these positive geometries. And then we can go all the way through and start to make predictions about particles. So I work with mathematicians, say, well, so what are the mathematical, surely someone has done this, with what's the relationship of Markov chains to decorated permutations, and turns out that there wasn't. So we did it. So
doing some
we
new maths, new mathematics.
Yeah, I work with a mathematician named Cheltenham Prakash, and so it's pretty easy for me to do new math when I'm working with a real mathematician. So hats off to Chetan and my other collaborators on this: Robert Prentner, Shwapun Chatterjee, Manish Singh, and others.
And so, Don, what will you be pumping in, if you like, at the sort of conscious agent end in terms of values, or what is it that will be pumped through that kind of bridge, if you like, into the all the way into the hadron collider or the particle itself?
Well, yeah. So what we found was when we actually wrote down these maps to decorated permutations, it told us 2 places to look in our theory, in the conscious agent dynamic. One is so-called recurrent communicating classes. So when you have a dynamical system, you have certain number of states, like 10 states. And if you're in state 1, there's a probability that you'll go to state 2, 3 through 10, and so forth. State you have a transition matrix.
It's like a Bayesian chain of some sort, is that?
Well, it's a probabilistic chain. It's not irrelevant. There is a connection with Bayes, really interesting. And this is something that's not well known.
Oh, okay.
And we're about to publish it. So we discovered it. There is a partial order on the set of Markov kernels. So all these little matrices, 2 by 2, 3 by 3, 4 by 4, billion by billion, quadrillion by, there's tons and tons of Markov. It turns out that you can order them, say when one matrix is less than or equal to another. And it's called a trace chain. There's a way of taking, to be very, very clear, if we have, say, a chain on only 3 colors, red, green, and blue. And I can say if my current color is red, then what's the probability I'll see green, red, or blue next, and so forth. But current is green, what's probably seeing red, green, blue next, and so forth. So you get a 3 by 3 matrix there of numbers, right? Now, what if you're watching that process and you're seeing the red, greens, and blues, and you say, I'm just going to, I don't want to look at blue anymore. I'm just going to look at the red and green and just pay attention to them. It's the same process, but I'm only paying attention to the red and green. Well, then if I looked at them long enough, I would get a new matrix. I would say, well, here's the probabilities if I see red now that I'll see green next, or if I'll see red next. And I can get a little 2 by 2 matrix, right? That's called the trace chain.
Right.
of bigger 3 by 3, right? So you
Yeah.
take the bigger one and you get absolutely new probabilities. It's not like it's not the same probabilities. They're very, very different. But
Right.
because so that's called a trace. And so you can take the trace of any size Markov chain on any subset of its, and our order is very, very simple. One Markovian kernel is less than another, if and only if it's a trace chain of the other.
Mm-hmm.
That gives you a logic. And now I mean, so you asked a question about Bayes. So this is deep.
My bad. Let's go.
This logic, this order gives you a logic. It has an and an or, and the what they call conjunction and disjunction.
Yeah.
And
Yeah.
the so the conjunction and disjunction then lead to different matrices. The conjunction will give you a new matrix.
Mm-hmm.
And so now it turns out each matrix has a probability measure associated with it, which is the long-term probability of each state. So like the red-green matrix would have probability that you see red, green, or blue, period. Whereas the new matrix, when you had to take the trace, would only be about red and green, right?
Mm.
So here's now finally the thing. The conjunction.
If it's a new object, what happens to the trace? Which trace does it?
Well, so they can only have a conjunction defined if they both have the same trace on the states that you're looking at. So if you have two, suppose I have two 10 by 10 Markovian kernels, but they only share states 1, 2, and 3.
Mm-hmm.
But they have to have the same trace on states 1, 2, and 3 for them to be able to have their conjunction.
Right. Okay. Okay. Right.
Otherwise, so this is not a Boolean logic.
Mm.
There's no greatest element, and there's no global negation. This is more general than quantum logics, the orthocomplemented modular lattices of quantum logic. This is more general than that.
Mm-hmm.
So we get a new logic that's really quite interesting, and then from this logic projects down to the logic of the probabilities, the stationary measures. So the long-term probability of seeing red versus green versus blue. Finally, I can answer your question. When I take two of these probability measures and look at the conjunction of the probability measures,
Mm-hmm.
that is a generalization of Bayes' rule. It turns out in our logic
Wow. So so Bayes has emerged from, again, you've generated
Bayes
Bayes from
emerges
it.
from this as a special case of the conjunction of the so-called Lebesgue logic of probabilities, which is a projection, a homomorphic projection from the trace logic of Markov kernels. So
Wow.
it's that you can see I couldn't just answer you right away.
Yeah.
Bayes falls out of this thing as there's a whole big structure that comes out of this, and so we're about to publish all of this.
That is super cool.
I just finished writing that section of the paper.
I hope you mind just brief interjection here. I can't help but think about Stephen Wolfram at the moment, because of course he's working on a project to try to kind of provide a sort of foundation that gives you relativity as an emergent property, and he talks about these atoms of space, and obviously he's got with his background in cellular automata, he's looking for something very sort of basic and fundamental to try to explain macro phenomena and so on. And I mean, is he going to this conference you mentioned? And I just wonder whether is there a dotted line here? Am I? Or...
Oh no, I think that you're in fact I'm scheduled to have a podcast with Stephen in early May, so we're going to have a conversation. It's going to be a lot of fun.
I can't wait for that. I cannot wait for that.
Me too. His work is brilliant. Of course, he's a genius, and his idea is different from mine, but similar enough that I think that we're going to have a lot of discussion. So where it's similar is that he's looking outside of space-time. He's looking, but where he's looking outside of space-time is what he calls the Reuliad, the space of
space is an emergent property, isn't it, of his system? So space itself has to kind of emerge And then I think he talks about these atoms of space that can give the appearance of being a particle and things like that. So some of the language in his thinking is inching away from the mechanistic, materialistic view, isn't it? So it seems like this revolution is kind of happening everywhere, if I might say.
That's right. And
Mm.
he's non-committal about the nature of these,
Mm.
rules outside of space-time, the rule he had. They're just
Mm.
algorithms. And
Mm.
so and I'll be interested to, question him about that, and I'm sure he'll be interested to push back on me about, what is the nature? Is he thinking about these things outside of space-time as unconscious automata, or how is he thinking about them?
Mm.
Because ultimately, as a scientist, we need to state our assumptions about the very nature of the fundamental entities in our theory.
Mm.
What am I going to assert about these?
Yeah.
And
What are my
so I'm
beables?
asserting that they're
Yeah.
conscious,
Yeah.
they have
Yeah.
conscious experiences. And I don't know if he wants to go there. If he doesn't want to go there, then he will inherit the hard problem of consciousness, and he will have to explain how conscious experiences
Mm.
arise from his
Yeah.
automata. So I'll be very interested to hear where he wants to go on that.
I've listened to a lot of his material lately on some of his sort of observer theory, and he's kind of
Yeah.
suggesting that things like entropy are far more linked with limitations in our perception than they are with the actual degradation of the system itself. And so he's kind of he seems to be involved in the game of turning things on their head as well.
And I
So
would agree
yeah.
with him on that as well. I mean, I think that physicists are also telling us, that local realism is false, that the
Mm.
act of observation is some sense creating what we observe. And by the way, the quantum physicists don't have a theory of observation.
Mm.
They will say that when you observe, you have what they call the collapse of the wave function, and they can write it down in terms of certain kinds of operators and so forth. But they can't. That's a nonlinear process, and the Schrodinger equation is linear, and they have no way of using Schrodinger evolution to explain the observer, which collapses to a single outcome. And you might say, well, but there's decoherence, and no, decoherence doesn't do that. It will take you from a complex superposition state to a real mixed state, but it will not take you to a single outcome. It can't do it.
Yeah.
So that doesn't do it. And there are other things that people say, and I'll just say quantum physics doesn't have a theory of the observer that works. And what we're doing in this trace logic that I just mentioned, so this trace order and the trace
Yeah. Yeah.
chains,
Yeah.
that's our theory of observation.
Wow. So that's
We're
what's going
saying
on.
this. We're proposing that this is a mathematically precise theory of observation. This is what happens in observation.
I think
It's a trace.
there's a few other things that you've talked about with the authors, sort of the mathematics around conscious agents that suggests that there could easily be sort of scaled up conscious agents that perhaps even a sort of metacognitive kind of human sort of conscious, or sort of, crazy stuff like that. So when you consider things like ants' nests, no one of those individual sort of ants really cognizes what's going on with the whole nest.
Right.
But we've shown that ants' nest apparently can be trained to do certain things, and so they're acting and learning as though there is a singular intelligence, one that we could potentially relate to. So could
Yes.
it be the
Yes.
case that there are higher order conscious entities? And I sort of heard it suggested that within your conscious agent model, there certainly could be, and they seem to be a kind of compound sort of maybe sort of superstructure, conscious superstructures, if you like. And maybe
Yes.
that's what's going on with what we see out there. The large planetary structures, are these the impressions or the appearances of kind of deeply complex conscious agency that we just can't engage with directly, if you like?
Yes, I'm on board with that with one little proviso. Again, the same proviso I gave at the very start, which is a theory
Aerospace.
is just a theory. And
Yes.
so
Yeah.
so my theory is not the final theory of everything, and it's not even close. So just with that, but given that, then I can say what is true within the confines of this theory.
Yes.
Whatever consciousness itself is, I don't know.
Mm.
This is as a humble scientist coming up with another baby step in science, then I'll speak about it in that way.
Mm.
So within this framework of conscious agents, yes, you can get arbitrarily large conscious agents, trillions, quadrillions, Google by Google matrices and so
Mm.
forth in this
Mm.
thing. There is no highest, which is really interesting to me. When this Lebesgue, the trace order on, so all of these different consciousnesses, and there are ones that are truly huge.
Mm.
There's an order on them, there's a logic on them. You can take the and the or, and sometimes you can't. Some of them you can't, some you can.
Mm.
So there's this huge logic. There's no highest consciousness in this. So there's no such thing.
So there's no Godhead. There's no kind of coordinating a single sort of narrative that contains it all.
That's right. There's no president at the top of this whole thing.
Mm.
There's no God, what we typically think of as the one kind
Mm.
of. So there's not the one, but there is the whole. And
Mm.
the whole is really got a complex logic. Locally, it's Boolean. And so locally, you can talk about the one, right? There's in this local Boolean logic, yeah, there is a greatest one in this one, and so forth. But globally, not. And but also to your point about an ant colony perhaps being a hint at a conscious agent as well. Absolutely, our headset, a space-time headset, is a dumbed down version of this network of conscious agents. So I'm always interacting with conscious agents according to this theory.
Mm.
So yeah, when I'm interacting with an ant colony, I am interacting with a conscious agent,
Mm.
and as it happens, my headset hasn't completely erased all the interesting stuff about that conscious agent. I get some hint of it. When
Mm.
I'm looking at a rock, my headset is erasing all sorts of information. And by the time I get to something I call a rock, it's erased pretty much all of the information about the conscious agent structure, that I
Mm.
might have.
That's interesting. You
That's
say
what headset.
erase. Do you think it is an active? You say erase it, or it's just not
It just doesn't
accessible?
show it.
It's just yeah, yeah.
It doesn't.
Okay.
It hides
Yeah.
it from you, like
Yeah.
your desktop on your computer. It's not
Yeah.
erasing information in your computer.
Mm.
It's filtering the information that comes to you.
Gotcha. Like the icons on the desktop sort of metaphor.
That's exactly right. Right.
Yeah. I think you sort of answer. I mean, you mentioned, I think, on a recent conversation as well that you've got particle physicists joining your game now as well. So you've actually got a particle physicist who's working on your research and so on. That lends credibility, I think, doesn't it?
Yes, I was actually delighted. Schwapon Chattopadhyay, who's a well-known particle physicist. He's worked at CERN and Fermilab for about 35, 40 years or something like that. He's teaching classes at UC Berkeley in physics.
Mm.
So he's brilliant. He approached us,
Yeah.
and because he'd seen a little bit of our work, and he knows that there's a lot of work ahead, but he thought we were on a good track. And so he joined us on a proposal. We have a proposal about testing our theory with actual data from particle colliders about quark gluon interactions inside of protons. And so he helped us frame those particular predictions and so forth. And he's continuing to work with us. So yeah, that's in fact the paper I'm writing now with my team on what's called Traces of Consciousness will be the title of it. Traces of Consciousness. It gives us trace logic.
Mm.
What we're doing is setting the groundwork to get explicit predictions about the momentum distributions of quarks and gluons inside the proton at all levels of what they call Bjorken X and Q squared, which are the temporal and spatial resolutions that they can look at the inside of a proton. And as you change the resolution that you look in space and time inside the proton, you see different stuff. At the lowest resolution, you see 3 quarks, 2 up quarks and a down quark, and some other smaller quark anti-quark pairs and gluons. As you increase the resolution, you then see lots of a quark anti-quark sea and lots of gluons. And then at the highest resolution is just a sea of gluons, just a massive. And so you get these momentum distributions. And what we're planning to do is, we still have some work to do. Even this paper won't get us all the connection we need to make the precise predictions, but you have to build one part of the railroad bridge at a time before you can drive the train across.
Mm. Mm.
We've got the decorated permutations. We're now getting the theory of observation with this trace, because the quantum theory doesn't have a theory of observation. We had to make one.
Mm.
So we got that. So
just in your spare time, Don.
it's but fortunately, if we can get the connection to the positive geometries, then they've built the
That's the
rest of the railroad
interface.
track.
You've kind of plugged in, haven't you?
Right, we've connected with them. So that's hopefully our next paper. We will finally nail down the connection with the positive geometries. In fact, I just got a gift, very, very kind gift from a foundation, to hire 2 postdocs, new PhDs in algebraic geometry who know these positive geometries and the
Wow.
relationship to particle physics. So I'm planning to get 1 or 2, to try to hire 1 or 2 new PhDs in mathematics to help us push it, because this is non-trivial.
Mm.
This is, I mean, it's actually
Yeah.
abstract algebraic geometry, and so we need a real expert, not
Mm.
just a particle theorist. We need a real mathematics expert to really make sure that the railroad ties won't send us off the track.
That's so exciting. And this is happening now. You're looking for these guys now, are you? You've
We're
got
going to
the
announce
advert.
it. The University of California has been doing
Yeah.
the paperwork for 3 months.
That's
We,
zippy,
we,
isn't
we,
it?
that's the way, that's the way it works for the university. It's a wonderful university. They dot every I, cross every
Mm.
T. So,
Yeah.
I
Yeah.
had this money 3 months ago, but it's taken 3 months to shepherd it through
Yeah.
the bureaucracy here. But you got to do things right.
You do.
And so when the university says that they've finished stamping everything, then in 2 or 3 weeks we'll announce it.
That is so exciting. Look forward to sort of seeing more progress on that. But that brings me to another question, Don, if you don't mind. It's to do with this idea that, let's say you make some real progress with this and you prove that connection, right? And let's say conscious realism then sort of enters the conversation more seriously. People saying, well, let's try and do some more with this. What would happen if we shifted our paradigm? If we managed to unshackle ourselves from the physicalist paradigm, what kind of science would we then be doing? Because I mean, I remember once you mentioned about sort of just going round the headset. You said maybe it's possible to just get to Alpha Centauri without. Could you talk a little bit about that? What kind of science would we do, and what kind of world could we end up in if indeed this was pursued with all vigor?
That's right. So first, I'll tell you what was already happened with the work that the physicists have done in high energy theoretical physics.
Mm.
Stepping outside of space-time and discovering these structures, they found new symmetries that are true of the scattering processes that you didn't see inside space-time. So
Mm.
already, and by the way, the mathematics is getting much easier. So things that you couldn't compute, it was just too hard, it would take a supercomputer too long. With
Yeah.
Feynman diagrams inside space-time, you can now compute trivially. Literally hundreds of pages of algebra can be reduced to 3 or 4 terms that you can compute by hand. So
Yeah.
you're already getting, like in terms of practical applications of science, you're seeing new symmetries, and the math is becoming simpler. So, I mean, it's actually enabling some scattering experiments to be done that we couldn't do otherwise because we couldn't compute them fast enough otherwise. So that's one thing.
Mm.
That's more modest. Here's the deeper potential. Think about it this way. The physicists have been like the geniuses inside a game, a super user inside a game, right? The wizard, like in Grand Theft Auto. I'm the wizard that can drive the car faster than anybody, know all the tricks inside the game, and so forth. And being a wizard is an amazing accomplishment. And that's what science has been doing. We've become the wizards of the game. We thought we were the wizards of reality, but it was just the wizards of our headset. Space-time is just our headset. So now all of a sudden we realize that there's outside the headset, there's whatever the thing is that's being projected into the game in our headset. Well, but the metaphor to think about here is, well, what's outside the headset in Grand Theft Auto? Well, it's a supercomputer with lots of software. Well, if you start to understand that software, you can change the rules of the game. If you are the software engineer who
You can
wrote
hack
that
the
software,
headset. Hack the headset.
you can hack the headset. You can make the wizard look stupid. You can give him a flat tire. You can take the gas out of his tank.
Yeah.
So in other words, as clever as we think we are with all the technology that we've got just from knowing, we've only done that inside we're wizards in the headset.
Mm.
But that's firecrackers compared to what we can do when we actually have access to the software that runs the headset, now the sky is the limit. You just can't think big enough about what you could do. So going from here to Alpha Centauri, which is the closest star, which would take, I don't know, 4 or 5 light years, I guess, through space-time.
Generational ships, wouldn't you, and stuff like that? Yeah,
that's right. And the nearest, the Andromeda Galaxy is like 2.5 million light years. We can't go to the Andromeda Galaxy. Even your great grandkids would be dead on the spaceship going to Andromeda Galaxy. But if we could go around space-time to the Andromeda Galaxy, then you and I could go. And so you can see, if we don't have to go through space-time, we can go around space-time. It's just like, I don't have to, in Grand Theft Auto, I don't have to take the car from A to B through the virtual world. In the software, I can just put it there. I can just change the location pointer in the software, and there's
so, do you know your Twitterverse analogy? There's this sort of, we could perhaps extend that a bit and say, well, you've got your connections, your existing connections, and groups of connections and categories of connections and so on and so forth. But is this like getting a bunch of connections that you had no previous network contact with or something? Could you hack the system so I get a load of contacts that I had no previous contact with, that kind of thing? Does that work?
It is that way, but one thing that this metaphor really warns us is, if you all you know is, I'm a wizard of Grand Theft Auto, and so I know that world, and there's no hint about what software is even like, or what supercomputers are even like. You're going to have to really think out of your Grand Theft Auto world box.
What kind of substrate could give me this?
That's right. So it's going to require genius. Really, so you just can't sort of make small extrapolations from the Grand Theft Auto world to the world of the supercomputer and the diodes and resistors and so forth. It's not going to happen. So you got to really, that's why science proceeds one funeral at a time. You need a new generation of young, eager minds that aren't quite as dedicated and committed to the old stuff, and are happy to show the old guys are wrong, to take it to the next level. So we're going to really need the younger generations to pop out of our old conceptual framework and go to deeper. And by the way, my feeling is that process is in principle never ending. There is no final theory of everything. This is infinite job security for scientists. Infinite job security.
All hail that. There was something about, I don't know how you're doing for time, Don, but there was something about, you've talked about, if space-time is not fundamental, and there's this realm that kind of projects into it, right, that presumably is a spaceless, timeless realm, right? And that's obviously hard for our intuitive, mammalian brains to sort of get our heads around. But you said there's a kind of a way, so this idea of a timeless dynamic, and you said that there is these sort of non-entropic dynamics. So whilst there's a dynamic, there is no sense of kind of decay or any sort of direction of travel. Could you possibly talk a bit about that? Because I clearly haven't understood it fully. It's a bit fiddly, isn't it?
Right. So when you look at Markovian dynamical systems, you can, of course, write down systems in which, as the system dynamics progresses, the entropy on each step gets bigger and bigger. You can do that. But you don't have to. You can write down systems in which, as the system evolves, the entropy at every step is exactly the same. And so there's no increase in entropy in that sense. But it's a theorem that and this is in a book by Cover and Thomas called The Elements of Information Theory. People want to go check me up. So Elements of Information Theory by Cover and Thomas, excellent book. And I think chapter 4 or 5, one of those chapters, they go into this. The very simple proof, 3-step proof, that if you take one of these Markov chains in which the entropy is not increasing step by step, it's the same at every step, and you take a projection of it by, say, conditional probability, where you lose information by conditional probability, then the resulting projected image of that dynamics will have the increasing entropy.
Wow, right.
So in that case, the increasing entropy is an artifact of the loss of information in the projection.
Mm.
So one thing that we're proposing is, if you think back, the arrow of time in our worlds, in our space-time, has been deeply tied to the second law of thermodynamics, right? The increase of entropy.
Mm.
So, and the idea is that in some sense, our arrow of time and the second law of thermodynamics, the entropy is always increasing, are deeply interconnected.
Yeah.
And so we'll call it entropic time. Now, that notion of time is, in evolutionary theory, the fundamental limited resource. Time is the fundamental limited resource. If you don't breathe in time, you die. If you
Mm.
don't eat in time, you die. If you don't mate in time, you don't reproduce. Time is the fundamental limited
Mm.
resource.
Yeah.
But what this point of view says is that time is not fundamental.
Mm.
Time, the notion of an arrow of time, is an artifact, entirely an artifact of projection.
Mm.
And that means, now I'm going to preface what I'm saying now next with this. As I said earlier, I love evolutionary theory. If you want to understand human nature and human perception in biological terms, we have no better theory than evolution by natural selection. So I am not panning evolution by natural. It is the best theory, and I would not suggest any other theory right now for understanding human. Now, having said that, every aspect of Darwin's theory depends on time. It's
Mm.
evolution.
Yeah.
And that's an artifact. So the whole thing, the whole structure of Darwin's theory is an artifact of projection. It's not a deep insight into the nature of reality beyond space-time.
Mm.
So beyond space-time, we could have dynamical systems of conscious agents that do not compete, that don't have limited resources,
Mm.
have no arrow of time,
No scarcity.
no scarcity whatsoever. But from our projection, what we see is
Mm.
competition, limited resources, and arrow of time. And
Mm.
every aspect of that is an artifact of the projection.
Yeah.
You can see why it's so important that we not get stuck on our current theories. It's very, very important to never say, I've got the theory of everything, because you're going to have to really think outside of your headset,
Yeah.
outside of your current box to get to the next level.
Mm.
This is, so I love Darwin's theory, but the next step, let's go of every aspect of it. It's not a small leap. It's
Mm.
every aspect of it is an artifact.
Yeah.
But what we have to do then, and after I get connections with physics, I want to then show a dynamical system of conscious agents in which it's all cooperative. There are no limited resources, but the projection gives me what looks like evolution by natural selection, nature,
Mm.
red, and tooth and claw. That would be so that's number. I'm not going there first. I want to go for particle physics because there I can make numerically precise predictions.
Mm.
I'm going after the particle physics first because that's, in some sense, the simplest and the most precise thing we can do. And I want to get ironclad evidence because I need really smart people to jump in on this. I mean, I know that there are people out there that can run circles around me and my team. As soon as we can get them in on this, then this thing will take off.
Mm.
So that's my goal.
Of course, I mean, they may even sort of push back and challenge some of your ideas around this as well. So it could be a
That's
kind of
part of the game.
healthy. Yeah, absolutely.
That's part of
Um,
the game.
just wondering what else I've got here in terms of questions for you, unless you had anything you particularly wanted to talk about. But I mean, obviously you've had there's connections with Bernardo Kastrup, isn't there? And I think you've had a
Yes.
couple of interviews, and I mean, it just looks like your ideas are so beautifully dovetailed. And I mean, Bernardo's a bit of a hero of mine. He sort of gives voice to some of my own philosophical intuition. You obviously you mathematize some of these ideas and actually look for empirical foundations for it, and so on. I just wonder if you could talk a little bit about where your work overlaps and where you might disagree. Is there any
Sure.
place that he goes that you can't quite sort of grasp, or just some thoughts on this?
Well, first, Bernardo is a good friend, and I've known him for many, many years, and have invited him on many occasions to come work with us because he has the technical skills. He's a philosopher,
Yeah.
PhD in philosophy, but he also has a PhD in some kind of engineering, I think. But I'm not sure. But it is a technical field.
Mm.
Um, so he's got two PhDs. He's brilliant. Our ideas are, I would say, 99.9%
Mm.
aligned, which is
Yeah.
why I asked him to come join our team to work on the technical stuff.
Yeah.
Um, So, but I can, respect that he wants to sort of first really take idealism to a more respectable place in the philosophy arena. He's,
Yeah.
I think, been doing that. He has a really interesting notion about consciousness and dissociation, what he calls the dissociation issue. So if we have some kind of deep one consciousness or whole consciousness, well, we can imagine that there are breakoffs, right? There's the breakoff into the Matt consciousness and the Don consciousness that are going back and forth. So even if there's one consciousness, somehow, I mean, I don't know what's in Matt's head, and Matt doesn't know what's in Don's head. That's why we're talking and asking each other questions, right? So somehow the one consciousness has dissociated itself into a Matt and a Don. So we would like a philosophical understanding of that
Mm.
dissociation process, but then ultimately we would like a scientific theory of that. So recently, I know Bernardo has been looking to integrated information theory and talking with
Mm.
Tony and Cope because he's been thinking that some of the properties of integrated information theory might help him get a more formal mathematical theory of the dissociation
Mm.
process. Now, I haven't talked with him about this yet, and I'm looking forward to. I think that probably won't work. And the reason is that the fundamental assumptions of integrated information theory are based on the idea that there is a unconscious substrate, and that unconscious substrate has to have certain properties for consciousness to exist.
Right.
So their postulates are about properties that an unconscious substrate must enjoy before consciousness can appear. Now, those seem to be just the wrong foundational. You're not asking the question from first principles. I have a mathematical model of consciousness. What is my mathematical model going to be about how it can dissociate itself? That would
Mm.
be the principled way of trying to get. But this is saying I'm assuming a non-conscious substrate to begin with, and principles about how an unconscious substrate could give rise to
Yeah.
consciousnesses. That's not that seems not. First, I think the assumption is false.
It still
Right?
faces the hard problem, though, doesn't it? So they've still got to explain emergence of consciousness from that system.
That,
So
that,
yeah.
that's right.
Mm.
And the assumption that is giving rise to those postulates, namely that there is an unconscious substrate to
Mm.
consciousness, is false.
Yeah, that's
And
right.
so you have postulates that have been given for a false assumption, a false
Mm.
base. And I think that's trying to build a house on sand, right?
Yeah.
So what I plan to talk with, I haven't had a chance to talk with Bruno about this, but I'll probably do it very, very soon.
Mm.
Give him this trace logic is a formal theory of the dissociation process. It's right there.
Right.
The conjunction and disjunction are precisely how you deal with the dissociation. So if I have two of these conscious agents and they are compatible, so I can take their join and make a bigger agent, well
Hmm.
then just go in reverse. How do I take a dissociation of the bigger agent?
Mm.
I just go back down to the ones that formed it by a joint. That would be one
Mm.
way to do this. So this trace logic gives you a completely rigorous framework for dealing with the dissociation process, and it tells you that there's no one consciousness at the top. There
Mm.
is no greatest element. It tells you that locally it can look like there's one, and you can do local dissociations,
Mm.
but there will be certain consciousnesses that are not compatible and could never be reunited. So you can't, some cases, you cannot undo the dissociation.
Mm.
There's no way to. So in other words, it gives you a very, very unexpectedly rich theory of the dissociation process. I didn't expect it. I'm not smart enough to have expected all of that. All
Mm.
we did was
It's like
say
a free gift, you know.
it was a free gift. The only thing we did was we said, oh, if one Markovian kernel is a trace of another, then it's less than it. We're smart enough to think about that.
Yeah.
But to realize that that's going to lead to this whole logic that would be
Mm.
dissociation, no, we're not smart enough to do that. That is just, after weeks and months of playing with this, we all of a sudden realize, holy, this math So
Mm.
we came up with that little hint about the math. The math came back and then it taught us. The math became our instructor. So I didn't really come up with the theory of dissociation. The math taught us the theory.
Yeah. There's a couple of interesting things here because that there's something about what you said there that there is no kind of single one, right? There is just the all, which is subtly different. And that sort of seems to go against the grain of certain religious and mystical insights that sort of tend to
Yes.
think of this, even if you're a pantheist or it's kind of there's an authority figure of some sort, the
Yes.
central guiding hand of the whole thing. And this has come up in my philosophical group lately as well, where we've been discussing idealism and sort of these dissociated boundaries and so on and so forth. And why did the one separate off into the many? But this question of metacognition, and there's a kind of leaning towards, we kind of feel that perhaps the one does have some sort of metacognition or awareness, and it somehow kind of reflects in on itself at that very high compound level. But you're saying that's not possible. So it's not possible for there to be a single kind of identity, if you like, of that kind of being. But there could be very large kind of conscious compound collectors and stuff that do have deeper insights into the nature of reality than others, though, right?
That's right.
And
So
could
first, I agree with you. And what I would say is, first, again, my theory is just a theory.
yeah,
So
of
I'm just
course, yeah,
telling you
yeah.
what this theory
I
says.
know this is speculation, but it's it's yeah.
But what you said about the theory is correct. You can get an arbitrarily large Markovian kernel.
Mm,
You can let the number of rows and columns go as close to infinity as you want. So there is no limit to how. So in that sense, it's unbounded.
yeah.
Effectively. But what's interesting is there are infinitely many of those.
So we're
There's
talking about
infinitely
sort of
many of those.
scales of a kind of a Cantor talks about this, does he? Sort of scales of infinity.
Then there's Cantor's hierarchy. So I was just
Mm,
doing within like Aleph 0 and Aleph 1 here, in Cantor's hierarchy. But ultimately, we even want to think about this in terms of, and now I'm way above my pay grade, so that's why I haven't gone there. I'll need my postdoc to help me on this. But I mean, Cantor has an infinite number of levels of infinity, right? Each level is infinitely greater than the other.
mm,
So when we talk about God or the one, whatever that word is pointing to, the reality
mm,
that word is pointing to is no less complicated than all of Cantor's hierarchy.
mm-hmm, mm-hmm,
And my own understanding of my Lebesgue logic and what it only goes to Aleph 1, right?
mm-hmm,
So
mm.
so that's just step one of an infinite number of steps. So I humble pi is completely in order for me at this. But at this, what I can say is the mathematics that we have so far tells me that all of our
Excuse me.
intuitions, our standard, there's one are just way too shallow, and
Mm-hmm,
the mathematics, when we actually take the ideas that the various spiritual traditions have been saying and actually turn them into precise mathematical, so we take their informal pointers and we turn them into precise pointers, then the precise pointers come back and they become your teacher. This is now where science and spirituality can have a profitable interaction. The spiritual traditions have for thousands of years told us that space-time is just a headset. There's
yeah.
something outside.
This is what I was
They,
going to ask you about, Don, actually. I mean, what do you think about those insights from the Upanishads, the Hermetic tradition? You could argue that sort of monotheism is founded on this idea of the one single mind and so on and so forth. And I don't know, any thoughts on that? I mean, and now we've got the
sure.
science that's sort of beginning to peel away the layers and say, oh, actually, maybe these guys are right. How did they have
Right.
those insights? How did they have those insights without the technical
That's a
stuff
good
we've
question.
got these days? I mean,
Well, so first, I think that they're on to something, that space and time are not fundamental. I think that they're right about that. And they're on to the idea that words are just pointers and teachings are just pointers. And, the Tao Te Ching says
mm,
the Tao that can be spoken is not the
it's
true
not the
Tao.
true down. Yeah,
And as soon as you understand that, then it's fair enough to read the rest of the Tao Te Ching, right?
yeah.
Because now you understand the right spirit in which to take it, which is the right spirit to take a scientific theory.
Mm.
The
the
same
limits of
spirit.
its theory. So the Tao Te Ching shows the limits of its theory.
That's right. And so I think that they're onto something there. Now, here's the limits of the spiritual traditions. Their pointers are extremely imprecise.
Mm.
They tell you that this is just a pointer, and don't take it, don't be, dogmatic about this pointer. It's just a pointer. And the teachers may have understood that. Most of the disciples don't, and we have religious wars and millions of people killed and so forth. What we need is what science gives, which are pointers that point to their own limits.
Mm.
Einstein's pointers about space-time tell you, by the way, space-time only works to 10 to the minus 33 centimeters, and then it's over.
Yeah.
And that's what I'm hoping now for this new movement to do, is to bring this kind of rigor to the spiritual ideas. And maybe this trace logic is an example of that kind of thing, where the notion of the higher consciousness. What do we mean by the higher consciousness? Well, that's just a pointer.
Mm.
Well, here's a more rigorous pointer. How
Mm.
about the trace order on all possible Markovian kernels as a lower limit on how complicated that thing has to be,
Mm.
right? It's not the final word, but it's certainly not any simpler than this. And when we look at this, already we're going to get blown away from all of our concepts that we had before that are going to look perfectly trivial compared to what this. And then hopefully in my lifetime, I'll see someone blow away the trace order with something that goes to Aleph, whatever. And so that's what I'm hoping to see here. So I think that there can be a rapprochement between science and spirituality. Both will have to give up something.
Mm.
The physicists and the scientists have to give up space-time being fundamental. But our own science is telling us that you better do that or be a dinosaur.
Yeah.
Spiritual traditions will have to give up certain things. I think we'll find that certain of their ideas are very valuable and useful. But when we mathematize them, we will get surprises and things that you don't like even. So when Einstein had his theory about general relativity, right? His big idea was that if I was standing on a scale, a weighing scale in an elevator, and all of a sudden someone cut the cord on the elevator, all of a sudden I would be weightless on the scale. That was his big idea. It took him years, but he wrote down the equations of general relativity from that and got the theory of gravity that made him famous around the world. Within a year of the time he published it, a guy named Schwarzschild sent Einstein a letter and said he found a certain solution to his equation. Black holes. Black holes come out. Einstein didn't know that. He didn't like it. He didn't believe in black holes. As smart as Einstein was, the equations were smarter in a way. The equations came back and even taught Einstein something that he didn't know about his own intuition about a falling elevator and a scale. He didn't know that it would entail there are black holes, and it does. And so what we're going to have is, when we actually get science and spirituality interacting, we start to get, for spiritual ideas, the rigor of pointers that we have in science. And we're going to actually find implications of those ideas that no spiritual teacher ever thought about, and some may not like at first. So it's going to be humbling.
Yeah.
That's what happens when we do this. We become humbled. But your other question was, how is it that we could have done this anyway? How did these spiritual teachers actually do this without this? And first answer is I don't know, but I'm here to speculate. I think that whatever the whole is, you are that and I am that, looking at the whole through a headset. And so the reason why people can do this is because we are not simple little intelligences that are dependent on 86 billion neurons to generate them out of unconscious ingredients. We are the other way around. We are the infinite intelligence that has decided to shoehorn itself into a little avatar inside a little headset of space-time. But the intelligence is still there. And as long as we don't identify with the avatar, we have access to that infinite intelligence and something
So
spiritual.
So sort of meditation, if we can somehow sort of unshackle ourselves from our kind of tactical, egoistic thinking, we can literally sort of look back in a way instead of looking at and sort of look at it and say, we've got access to. You're saying we have access to that through meditation and so on.
That's right. And in fact, I use that all the time in my research. I run against a wall, and I'm not smart enough with, the avatar in this headset is not smart enough. So then I spend time, I just go into silence.
Mm.
Sometimes I get something and sometimes I don't. But I would say this, that the reason all of our genius is really from that infinite whole intelligence. That's where it comes from. And this body is just the avatar. So I'll be very, very explicit. Just like in Grand Theft Auto, when I see the red Ferrari over there, the red Ferrari only exists when I render it, when I see it, and it doesn't exist otherwise.
Yeah.
Same thing is true of my body. Same thing is true of my brain.
Yeah, and that's quite it, because the body is kind of part of that external world as well, in a sense, isn't it? You know what I mean? If I
it's just
this
an icon.
Isn't my body. This is just part of that world that I'm peering into.
That's exactly right. I'm appearing in the headset and I'm seeing something that I call Don's body or Matt's body. And sometimes I appear and I see things that I call, Don's neurons, or I do a brain scan. But those neurons only exist when I perceive them. They don't exist otherwise. Neurons cause none of my behavior. They cause none of my intelligence. None of it. What is my intelligence? It's the intelligence of the whole. It's been shoehorned into this little interface. Apparently, the whole wants to look at itself from different perspectives. Let me look at it from this perspective. Now I'll look at it from, and space-time is just one of an infinity of different perspectives. The theory of space-time is not the theory of everything. It's a theory of one out of an infinite number of different perspectives.
Again, here is where mathematics does some work for us, because as you suggested as well, we can use mathematics not to visualize, because we can't because of our constraints, but we can conceptualize n-dimensional space. Infinite dimension, and we can do the mathematics there. I mean, what does that say for you about the nature of reality? That whether we're working in space-time, whether we're working with non-spatial entities like amplituhedron, there is this formal language for describing phenomena, or whatever it is. I mean, and like you said, it has implications that we didn't intend. It's the mathematics showing us. It's Einsteinian mathematics showing Einstein that the singularities are going to merge and so on, and he doesn't like that. So what are maths? What are mathematics?
Well, that's a fantastic question. Here's just an informal answer. I think of consciousness, or the whole consciousness, as the living organism, and the maths is like the bones of that living.
Yeah.
But so maths are unbelievably beautiful, and they put a lower bound on the complexity and brilliance of the whole. But I imagine the whole transcends mathematics infinitely. But even the math, Gödel's incompleteness theorem, what it tells me is, what it says is, you give me a set of axioms, and there'll be an infinite number of theorems that they can prove. But there'll be theorems that they can't prove, and they'll tell you this cannot be proven within your set. You can say, well, I'll just take that as a new axiom. And that's fine. But then Gödel says, well, so now you've beefed up your axioms, but now I'll show you a new thing that you can't prove. And this thing can't be proven by that. The structure of Gödel's proof says to me that goes on infinitely often. That means any formalization of mathematics leaves out an infinity of truths, an infinity of mathematical truth. And even the completed mathematics would leave out an infinity of the whole that transcends mathematics. So what mathematics does for us is it gives us ways of taking perspectives on the whole. And the mathematics is so brilliant that it can tell us the limits of that perspective. Gödel's kinds of incompleteness, or the kinds of incompleteness that I was talking about, that the physicists have found about space-time. The mathematics, it falls at 10 to the minus 33 centimeters, falls apart. The mathematics is there to tell us This is a wonderful perspective. You can do a lot of stuff with this perspective. Oh, and by the way, here's the end of this perspective. This is where it fails. And so the dilemma that we have as being the infinite intelligence is, if you want to know yourself conceptually, you can't. The conceptual thing can only give you a perspective, and a very limited perspective. But if you really want to know the infinite intelligence that you are, then silence is the only way.
Wow. So, gosh, that just blow my mind there completely. That's no, that's really interesting. I mean, one of the things that's occurred to me about the mathematics, because of course, once you've got, you've done your pre-spatial mathematics, bridging from conscious agents, amplituhedron, and so on. Obviously, those models are still just models that represent some underlying phenomena. So I was wondering if I could ask you what you think. I mean, I know you could say conscious agents, but can you say anything else about that which is being modeled by these pre-spatial kind of mathematics?
Well, yes, in terms of the conscious agent dynamics, what I think we may be able to show is that if you look at all possible, say, 10 by 10 Markovian kernels, right?
Yeah.
They form a polytope. It's a Markov polytope of 10 by 10 kernels. And it has the Markov polytope of n states, I think has n to the n. Yes, n to the n vertices. Yeah.
It says like sort of all play, or it's like sort of all play, all kind of round robin kind of.
That's right. And so so by the time you get to only just 50 states, a Markov kernel with only 50 states, the number of vertices so you're now asking, describe all the possible, just 50 by 50. And by the way, you can see millions of colors. 50 is nothing. 50 is trivial. Absolutely. But just look at 50 colors. The Markov polytope for the possible dynamics of perception of 50 colors, the vertices on that polytope, there are more vertices than the number of particles in the known universe, in the visible universe. That's how many vertices there are. So this thing blows up incredibly quickly.
Yeah.
But my guess is that the relationship between the complex mathematics of consciousness in the CA theory and these positive geometries, and if I knew the answer, I wouldn't need to hire this postdoc that I'm talking about. So here I'm just going to say I'm probably flat out wrong in what I'm about to say, but I'll speculate, and I'll probably say this to the postdoc, and the postdoc will laugh, and then they'll show me the right way to go.
This is what tenure's about.
They'll say what it's about. Yeah. Somehow there's a mapping that takes volumes of the Markov polytopes and maps them to volumes in these positive geometries. They
Right.
project down. So I'm betting that volumes in the Markov polytope project down to volumes inside these positive geometries. We just need to understand exactly which volumes get mapped into which volumes, and
Right.
we've got it. So it's possible that the postdoc gives me that in the first week, and they're free. I mean, they did what they needed to do. I'll just have them help me on the other stuff. But
Yeah.
the big project may not be a 2-year project. Maybe if someone actually knows how to think about this, it's a 1-week project. We'll see. But it may be, maybe it's deeper than that. I'm just not smart enough to know.
Hence the postdoc. Don, I mean, unless there's anything you particularly want to sort of discuss now, I think I better crack on actually, because I've got to make a journey to go and see my daughter. So, but I've really, really enjoyed this conversation, and thank you so much for coming to talk to us. Brilliant.
My pleasure. Thank you so much, Matt. It was a great conversation. So
Yeah,
thank you
really,
very much.
really, really enjoyed it, and I'll try and keep up the email contact, and if I'll keep abreast of your work, and any further questions, I'll wing them across.
Okay, very, very good. Okay, take care.
Thank you very much, Don. Take care.
Cheers.